Today we'll show how to build a factorial morphism using basic functions like add and multiply, and categorical operators like composition and products and coproducts. We will generate C++ code for double precision floating point, compile it, and run it. Next, we show a novel diagrammatic way to build morphisms using what are herein referred to as reference morphisms using injections and projections. To generalize the notion of factorial, we create the definition of factorial in Catecon. Lastly, we use that factorial definition to generate a 128-bit version of the factorial and run it as well. Let's get morphing. We're referencing a pre-existing diagram called CPP that we use for accessing basic functions like subtraction and multiplication and accessing the TTY console. First off, let's list the basic required pieces. Use X to change the input mode to morphism and double-click. Our first factorial uses double precision floating point, or F64. Call our morphism fact, and of course the codomain is F64. To assemble using categorical operators, we need the basic bits that we're assembling, and there are 4 things we need. Test for 0, the number 1 for doubles, a decrement by 1, and the 64-bit floating point multiply. Our first step then is to copy F64 and create the identity morphism with a double click. We know we're going to use the input to test for 0, so we need to make a copy of the input by creating a factor morphism, or delta in this case, from F64 to F64 across F64. Next, select the test for 0 and the identity and create the product of the two by clicking the P key. Drag the domain and drop on the codomain to fuse the two together. Select the codomain and note the appearance of this special button. Catecon comprises a list of actions, and those actions appear on the toolbar depending upon what has been selected. As it happens, we are in a category with distribution, and we have selected something we can distribute, so click. We can only write distribute, so click. Now we need 2 morphisms that depend on the result of the test for 0. We do not have something labeled true and false, but we do have coproducts and a terminal object. Hence, we represent the space of truth values with 1 plus 1, sometimes known as 2. False corresponds to the 0 injection from 1 to 2, and true being the 1th injection from 1 to 2. For the distribution, we can also look at its string graph to see how the various factors of the domain and codomain are connected. Our 2 new morphisms need a domain of 1 cross F64, so select 1 and F64 and hit the P key to create their product object. For the morphism corresponding to the true path, we don't need the F64, so we double-click on the 1 factor to create a projection to it. Next, make a copy of the floating point 1 and fuse the domain. Area select both morphism and notice the composition icon appears now that we selected something composable. Make the composite and we have the first of our 2 morphisms. Now make a copy of the 1 cross F64. This time we need the F64, so project the F64 and forget the 1. We need again to make 2 copies of our input, so bring a copy of the delta morphism over and fuse it. Next up is doing the recursive function call, so take 2 copies of the decrement and fact morphism, fusing in the proper order. Select both and compose. Select the F64 identity and the last morphism. Form the product of the 2 and fuse appropriately. Select the multiplier, copy, fuse, and compose. Now we have our second morphism. First, select the latter morphism and it represents the false path, and then select the former morphism as the true path. form the coproduct of the two, and fuse appropriately to where we left off. Lastly, in the composite, we need to fold the two paths in the coproduct together. Select F64 and the dual of the projection button to create the fold. Select and compose. Now we have our main morphism built. Next, select the fact morphism followed by the main morphism. Our toolbar now shows a new option for recursion, since it was detected that the first morphism has the same domain and codomain as the latter, and the latter uses the former somewhere in its construction. Click it to set the recursor, and we have finished creating the factorial as a morphism. But does it do anything? Let's convert it to C++, compare it to our original code, and try it out. Copy fact, and then select its domain and the right HOM object icon to see which morphisms have a codomain of F64. There's a lot, so we filter to find the morphism from standard input. Similarly, click on the left object icon to see morphisms with domain F64, and filter to find the out to standard output. Arrange and compose. Click on the question mark icon for info about the element itself. You will see a C++ option, so click it. Then click on the download button to get the C++ code for the morphism. And let us take a look. The first set of include files come from the C++ generator, and the subsequent ones are those from the reference diagrams. We have a couple of type defs. The first is 1 + 1 type def as bool, and our F64 type def as a double. Next up is the long internal name of our main morphism. This big long name is the unique name for the morphism in Catecon space of morphisms. In the emitted code, the function is seen as fun underbar its signature. An element's signature is a key internal feature of how Catecon tracks elements, and it is exposed here. We see this function calls itself, so it is recursive. It is also seen called from the program's main function, as it is called to read in a double, apply the factorial, and send the result to standard out. The function has an input of var2, and there seem to be a lot of variables. But where did these variables come from, as there are no variables in the original diagram itself? Go back to the diagram and click the G key to see all morphism strings graph if it has one. We see the connected string starting from our domain, continuing through the distributor and down into the true and false cases. This connected string through all the morphisms is assigned to var2. The propagation continues through all morphisms, even fdecker64 defined as a composite in a reference diagram. In effect, some morphisms appearing in the top-level expression are all expanded and do not have corresponding function calls. The main fact morphism has a function call as it needs to be recursive. Going back to the code, the var4 holds the result of the test for 0, and it looks like when true that the final result var3 is set to 1. Otherwise, var2 is decremented by 1, sent to the factorial, and the result multiplied. The remainder is boilerplate to read a number, apply it, and show the result. Go to the command line and compile the fact64.cpp code. No errors. Good sign. I have a script to run a.out with inputs up to 200, so run it. That looks good, though it switches over to floating point at 10. Keep going, and it looks like it overflows at 170 factorial. That was a bit of work, though in a pleasing categorical ASMR manner. Let us try to reduce the amount of work by using some injections and projections as references to guide the morphism assembly process. We start with the test for 0 morphism. Double-click on the left 1 for false to create an injection to that factor. Click the R key to turn the morphism into a reference. Good. What is a reference? Think of a reference as flowing in the opposite direction of the arrow. In other words, if the codomain is hit, try to run all the morphisms based on the domain. Now on the it is 0 path, taking a copy of 164 and fuse the domains. For the other path, take a copy of F64 and click the 1 key to create a morphism to the terminal object. Turn it into a reference and fuse the codomain. Next, double-click on the F64 to create an identity. Turn it into a reference and fuse. These two references mean that when both are satisfied, morphisms with domains on the F64 can then be evaluated. Take our decrement and fact morphisms and put them inline appropriately. Copy the multiplier and double-click on the first factor to project it. Turn it into a reference and fuse. Double-click the second factor and act accordingly. Now we can fold the two paths back together by copying down the F64 fold. Double-click to create the two injections and fuse. These are not references as the information flow is down the arrow. We can now select an object on our blob and the toolbar shows the Morphism Assembly button. Clicking the Action button then assembles the blob into a morphism. The resulting composite morphism has a similar structure to the one we created by hand. We make 2 copies of the input, run the test for 0, distribute, have 2 conditional morphisms, and finally fold the result. We have a few more factor morphisms in the composite as the general case goes through some subcases. Now look at our fact morphism and remove the hand-built morphism previously set as its recursor. Set the newly generated morphism as our recursor, and now we have the factorial morphism generated from diagrammatic references. Well, that was fun. What if I wanted to make a 128-bit version of Factorial? Instead of having to make a similar diagram each time there's a need to make a new factorial, we instead create a definition of Factorial. With that said, select Fact, notice the Definition button, and click it. The definition action scans the fact morphism and determines that the following morphisms are required to build the fact morphism. At the end, we see the morphism that can be generated by the definition. This is a simple or lower-level version of a definition, as we have not put any constraints on the required morphisms, and such constraints would be declared commutative diagram cells. Call our definition factorial and create it. Look at the definition and view its internals. We see the 4 required morphisms and fact morphism as before. Now use the definition to create a 128-bit version of the factorial. We enter the names of the 4 corresponding morphisms for F128 and create the morphisms. With the morphism selected, note that we have a button indicating the presence of user actions. When we created the factorial definition, it creates a user action that looks into the selected elements to see if there is a match to that definition. In this case, we have something and can see the hdol/factorial action available. Click it. Now we have a listing of the original 4 morphisms as the source, and the 4 selected morphisms as the target. At the bottom are the morphism templates that can be generated. Probably should filter out the decrement. By clicking the replacement button, we get the F128 version of the factorial generated by replacing each occurrence of the source with the corresponding target. We want to test this new version, so we attach standard input and output to the morphism. Download the C++ code. Let's diff the fact64.cpp and fact128.cpp code. Basically, the names are different as they, at the least, have different domain and codomain. Signatures are, of course, different. The new variables are instantiated with 128 bits. The structural part of the code is the same in both files, as those lines don't show up in the diff. Let us compile the new version. Yay! I have a pre-existing script to run 8 out from 0 to 10,000 by 10. We run it and see that the first floating point number at 10. And it looks like we overflowed just before 1760 factorial. Quod erat demonstratum. Factorial as morphism.